Hola, muy buenos días a todos nuevamente. Hoy nos preparamos para presentar nuestra séptima charla técnica, abarcando una nueva aplicación de las múltiples aplicaciones que tiene el hidrógeno. Hasta ahora hemos hablado de cogeneración, transporte de carga, metanación, calor industrial, compresión, almacenamiento y equipos de generación de hidrógeno, los electrolizadores, hace 2 semanas atrás. También quería comentarles el resultado de un apoyo técnico que nosotros, que como GIZ, lanzamos en agosto. Finalmente se adjudicaron 2 proyectos, uno de transporte de pasajeros y otro de generación dual estacionaria. Así que estamos muy contentos y además pudimos lograr a través de cierto mecanismo de apoyar 3 proyectos más para donde vamos a definir los costos y la implementación de los sistemas de generación de hidrógeno, o sea, la parte de la electrolización, en el lugar donde ellos están funcionando. Así que nos tiene bastante contentos los resultados, bastante contentos también con toda la información que ellos nos entregaron y nos da una sensación que estamos avanzando en ese sentido. Esto nos permite conocer y ayudar un paso más en la concreción de los proyectos de hidrógeno, y algo muy importante, que ese hidrógeno de estos proyectos, la mayoría de estos proyectos son producidos en Chile para ser utilizados en Chile. Así que eso es una muy buena señal. Quería mencionar nuevamente nuestra contraparte, el Ministerio de Energía, que apoya estas charlas, así como nuestros colegas de Asociación Chilena de Hidrógeno, HO Chile, Universidad Técnico Federico Santa María, Centro de Energía de la Católica, un Comité Solar e Innovación Energética de Corfo y a la revista Electricidad. Como para dar contexto de la charla, en agosto de 2020, la capacidad instalada de generación en Chile era de 25,3 gigawatts, de lo cual el 51,7% corresponde a centrales termoeléctricas a carbón, derivados del petróleo y gas natural. Esta última corresponde al 18,8% de la capacidad instalada. Eso significa que tenemos un gran parque de gas. Las turbinas a gas pueden funcionar con una variedad de combustibles y actualmente el combustible más común es el gas natural. Para lograr la descarbonización de este tipo de generación, el hidrógeno podría presentarse como una gran alternativa. El uso del hidrógeno como combustible para turbinas de gas se ha demostrado de forma comercial, pero existen diferencias entre el gas natural y el hidrógeno, que deben tenerse en cuenta para utilizar el gas de forma adecuada y segura en una turbina a gas. Es necesario comprender las características de la combustión y controlar la mezcla y el comportamiento de aire, entre otras consideraciones. En términos medioambientales, una turbina de gas por sí sola no es suficiente para lograr la tecnología de combustión de hidrógeno sea 100% renovable, sino que toda la cadena de valor tiene que ser renovable. Entonces, este energético, en el caso del hidrógeno, tiene que ser producido a partir de energía renovable para que la cadena completa sea hidrógeno verde. Como hay muchos aspectos relativos a la generación de energía con hidrógeno, es que pretendemos ahondar en el conocimiento de las turbinas que pueden combustionar o aceptar hidrógeno como combustible, entender las ventajas y los desafíos que esto tiene, así como cuál es el futuro de las plantas de generación a gas. La generación renovable planteó una forma distinta de proveer energía y ahora el hidrógeno nos proporciona una alternativa para los sistemas de generación térmica. Para entender cómo será la transición de estas tecnologías, es que gestionamos una charla técnica con uno de los fabricantes más importantes de turbinas en el mundo, General Electric Gas Power, para que nos muestre el desarrollo tecnológico realizado por General Electric para el uso del hidrógeno en turbinas y su visión de cómo se desarrollará esta industria a futuro. El presentador de esta charla es el Dr. Jeffrey Goldmer, director de tecnologías emergentes en General Electric Gas Power. El Dr. Goldmer es responsable de desarrollar y ejecutar estrategias para la descarbonización de la generación de energía con turbinas de gas. Anteriormente fue director de soluciones de combustión y combustible para turbinas de gas y gerente de laboratorio de sistemas de combustión en el Centro de Investigación Global de General Electric. El Dr. Goldmer tiene más de 25 años de experiencia centrada en la investigación y el desarrollo de nuevas tecnologías, con un enfoque en los sistemas de combustión y combustible. Ustedes pueden, en la página de General Electric Gas, van a ver una parte de hidrógeno, pueden ver al Dr. Goldmer también explicando el detalle del hidrógeno. Antes de unirse a General Electric, el Dr. Goldmer fue investigador asociado de la NASA, donde realizó experimentos de combustión a bordo del laboratorio de gravedad reducida de esta institución. El Dr. Goldmer recibió su PhD en Ingeniería Mecánica en la Universidad Case Western Reserve y en Ingeniería Mecánica en el Worcester Polytechnic Institute. Ya, la presentación será en inglés, como todas las presentaciones anteriores. Por favor, hagan las preguntas por medio del chat, por favor, en español. Nosotros las vamos a traducir, ¿ya? Es más fácil para nosotros entender muchas veces la idea en español y nosotros la pasamos al inglés. Y finalmente, en la sección preguntas y respuestas, se la hacemos llegar a Jeffrey. Jeffrey, please turn on, the screen is yours. Please go ahead.
Rodrigo, thank you for the very warm welcome. So I want to thank everyone for joining us this morning. I'm very honored and privileged to be here. For the next 45 minutes or so, I'll be talking to you about the use of hydrogen and gas turbines. I do want to start for just a few moments and talk about the General Electric company and the gas power division of that company, which I work for. So for those who are familiar with General Electric, we have over a century of innovation in the world, including in fields of medical technology devices, aviation, power. In many parts of the world, the name General Electric is synonymous with aviation, synonymous with innovation. Many people are very familiar with General Electric because of just the use of the light bulb in the home. So I hope for those who are listening in, the name General Electric for you is synonymous with innovation and world-leading technology. Today, the company has 4 focal points: power generation, both gas turbine and renewables, our aviation division, and our healthcare division. Each of those brings incredible technology to the world. But as I said, I represent the gas turbine division, which today is known as GE Gas Power. This is a multinational company, spans the world, and we primarily develop power generation through the use of gas turbines, steam turbines, generators, heat recovery steam generators, and combined cycle applications, as well as the associated digital control systems that make it all happen, and a world-class field installation and services organization. What we like to say is that we engineer cleaner, more accessible energy that people depend on, powering growth and prosperity everywhere in the world. As you can see from this infographic, the number of ways that we impact the world, whether it's through the amount of electricity we generate, the number of people who are employed by General Electric, the technology we develop around the world. So I hope for those who are familiar with General Electric that this resonates true. But the focus today is on the use of hydrogen for decarbonizing power with the use of gas turbines. And that's what the rest of the presentation will focus on. But I do want to spend a moment and just reflect on the fact that as we think about decarbonizing and using gas turbines, there's more than one way to do so. We can think of this as changing the fuel that goes into the gas turbine and making the fuel either have zero carbon or renewable carbon. Or we can look at this by removing the carbon that might be emitted by the gas turbine in some sort of post-combustion process. On the pre-combustion side, we can talk about the use of hydrogen. And there are many different ways to use hydrogen, and the way people talk about that today is they assign a color to it. Green hydrogen would be hydrogen from renewable energy, electrolyzing water. Blue hydrogen typically denotes hydrogen generated from natural gas through a chemical process where the CO2 is then captured and either used or stored or sequestered. Biofuels obviously would be recycling carbon through a natural cycle, but there's also discussion about creating a synthetic methane that is using hydrogen that would be green, but then using some type of carbon, not from fossil fuels, but carbon again from some sort of recycled process to make a synthetic methane. On the post-combustion side, there are many technologies that can be used to remove carbon from the exhaust flue or exhaust gas of the turbine. Carbon capture systems have been around for a while commercially in coal systems, but they haven't necessarily been applied to gas turbines. So although we're going to focus primarily on hydrogen and its impact, I did want to take a moment and reflect upon the larger continuum of technologies that are out there to use with gas turbines as we think about decarbonizing. But let's really focus on the use of hydrogen. Let's talk about the experience that we have with hydrogen. What are the capabilities of gas turbines? what's the combustion technology that's really needed, and finally we'll wrap up in a conversation around what does it mean to put hydrogen into a gas turbine from the plant level. It's not just the gas turbine we have to think about, but we do have to think about the entirety of the gas turbine combined cycle plant, or the gas turbine plant, and all the ways that hydrogen could impact it. So the first thing I want to do is take a moment and talk about the differences between hydrogen and methane. Again, methane is the primary gas in natural gas. Typically, natural gas is composed of anywhere between 85 and 95% methane. So its chemical characteristics and combustion characteristics matter significantly. We want to compare those to hydrogen. So we'll start off with the second line in this chart, the molecular weight. Hydrogen is a lighter molecule. It's therefore a smaller molecule. And although we have systems where we use natural gas or methane that don't leak, putting hydrogen into those same systems could create a leak hazard. Hydrogen's flammability characteristics, that's the first line that's in bold, differ from that of methane. And upper and lower flammability limits really mean what's the lower mixture concentration and upper mixture concentration that hydrogen will actually burn in air. And you can see the lower end is about the same as methane or natural gas, but the upper end of hydrogen is significantly different, meaning that if you have a mixture of hydrogen and air, it will burn at a much higher concentration than methane would. And again, that creates concerns about safety should we have a hydrogen leak, especially in enclosed spaces. The next line says flame speed. Flame speed is a proxy or a term we use representative of reactivity of the fuel. So you can see here, although the absolute numbers don't matter, hydrogen's flame speed is about 10 times larger than that of methane. And therefore, it's about 10 times more reactive. We have to think about that as we configure a combustion system to operate the way we want to reliably. Hydrogen will burn hotter than methane, and that has implications around the production of NOx or NOx emissions. It also has a different heating value. So its energy density on either a mass or volume basis is different. And again, that has implications as we think about moving hydrogen through pipelines. On a volumetric basis, it's 1/3 as energy dense as natural gas, which means to carry the same energy density, our pipes could have to be bigger. So we have to think about all of these fundamental differences as we think about using hydrogen not just as an energy carrier, but as a fuel for power generation. So I want to spend the next few minutes talking about kind of where does hydrogen as a fuel sit in a spectrum of other fuels, and a little bit about experience. So the chart I'm showing here, and let me just start by explaining what it is. I'm plotting the heating value of the fuel. On the vertical or y-axis, I'm plotting it on a per mass basis, so kilojoules per kilogram. I've divided by 1,000 just to make the numbers on the scale a little easier to read. On the x-axis, I'm plotting the energy of hydrogen on a volume basis, so kilojoules per cubic meter, again divided by 1,000 just to make the numbers on the scale easier to read. And I've divided the chart into 5 zones. The first zone, number 1, is natural gas, LNG, methane, and shale gas. These are all gases that are predominantly methane. Now, if we want to think about the use of higher molecular weight hydrocarbons like ethane or propane or butane or LPG, we would move to the right on this chart, where the large number 2 is. Now, what we're talking about today is hydrogen, so we want to focus on a different aspect of the chart. So if we reset ourselves to that natural gas zone number 1 and move to the lower left on the chart, you can see we pass through a region labeled number 3. This is a region of fuels that we call medium BTU fuels. Some will call them medium heating value natural gas fuels or lean methane fuels. These are naturally occurring fuels where methane is no longer, let's say, 80 or 90% of the fuel, but it's more like 60 or 70% of the fuel, and the remainder of the fuel might be nitrogen or carbon dioxide. If we continue moving to the lower left on the chart to the number 4, this is where typical process gases live. So these are gases that you might get out of a steel mill. They're called coke oven gases or blast furnace gases. The process known as integrated gasification combined cycle, IGCC, where you take coal and you gasify it. The result is something called syngas. It's heating value tends to live in this lower left corner. Waste gases from refineries or other process plants tend to live in this corner. These are fuels that tend to include some amount of hydrogen, 5%, 10%, all the way up to 60 or 70%, but then typically have maybe a little methane and then some nitrogen or CO2. But you can see these fuels have a heating value that's something on the order of 20% of natural gas. On this scale, we'd be talking about 10,000 kilojoule per cubic meter, whereas natural gas is going to be much richer. Now, the reason I point this out is imagine you go back to natural gas and you start adding hydrogen to it. What happens if we just ignore changes on the vertical axis, as I add hydrogen fuels to natural gas, you can see on the chart we start moving towards the left. What that tells us is all of our experience working with these industrial fuels, these refinery fuels, these process fuels, everything it's taught us in terms of how we handle the fuel safely, how do you design your accessory systems, your valves, all of those lessons apply as we work with hydrogen. Now, I've highlighted something here that's very important. So as you add hydrogen to natural gas, you will absolutely start to reduce the amount of CO2 you create. But because of differences in the energy densities on those fuels, it turns out that to get a 50% reduction in your CO2 emission, you actually have to put in 75% of your fuel has to be hydrogen. Now, this is on a volumetric basis. I have a chart that will help explain this a little bit later. But again, just think about here for the moment, the concept of adding hydrogen to a gas turbine isn't a new phenomenon. It's actually been done for decades. And here's a chart that just gives you one sense of that. Now, these are all projects that General Electric has done. General Electric's competitors have done other projects as well. And so there's a rich history in the industry of using hydrogen-containing fuels for power. General Electric's experience goes back more than 30 years. One of our first large commercial projects was back in 1988, working with the U.S. Department of Energy. And you can see here through this timeline that we've continued to do projects in this fuel space even through the last few years. Now, what's amazing here is if we think about the type of gas turbines that we've used, they're not all one type. We've used smaller industrial gas turbines. We've used aeroderivative turbines. We've even used some of our larger, what we call F-class gas turbines. So we've really covered the spectrum of gas turbines in this space. So it's not just small industrial type gas turbines. And as you can also see, we've done work all around the world. This is a fuel type that's not limited to just one geographic region. There are projects in the US, there are projects in Europe, there are projects in Asia. We even have a project, I don't think it's listed on here. We've had, yes, it is. It's a project in Brazil. So we really have done work all over the world. So this is not, again, not a new phenomenon. It's been ongoing for many, many years. And the kind of statistic I like to give from at least a General Electric perspective is if we totaled all the units that we have supported over this 30+ year period, that represents more than 75 gas turbines. And these gas turbines have accumulated more than 6 million operating hours on these fuels. So again, this is not a new phenomenon, this concept of using hydrogen to make power. What's new in our world today is that we're thinking about using hydrogen explicitly made for power. Again, we've talked about this just a little bit on the last slide. This is a little more specific data, right? At least from the GE perspective, as we look at how we've used these fuels across our different gas turbines, as we use them in different application spaces, and as we've used them in different parts of the world. GE also prides itself on being a leader in this space. This is third-party data from a group called McCoy. Just shows that GE has received more awards and more units by more megawatts of awards in this space. So again, we pride ourselves on having industry-leading experience with using hydrogen and other similar low heating value fuels. I want to talk through a couple specific examples. I think they're important as we think about the use of hydrogen for power, because we can think about this in two scenarios. One where you have a gas turbine, maybe a new gas turbine, existing gas turbine, and you get some amount of hydrogen available to you, but it's not enough to fully load the gas turbine. So you might want to start blending hydrogen into your natural gas and using that to slowly start reducing your CO2 footprint. And the other extreme is you have a very, very large amount of hydrogen available to you, and really you do want to run your gas turbine primarily or completely on hydrogen. So I have 4 examples here for you. The first 2 on the left are in that initial scenario where you're going to blend hydrogen into existing natural gas. We've done multiple projects with customers around the world where they've had some fuel and it has had some amount of hydrogen, and we've blended that fuel in with natural gas. That requires some special hardware to do the blending so that you actually have control over the ultimate mix of the 2 fuels. The example second from the left, where you can actually see some piping, that's a scenario that we did about 10 years ago on an F-class machine where we actively blended hydrogen into the natural gas and brought that to 4 gas turbines at a site in the US. Now, the other extreme we talked about is what if you happen to have a source of hydrogen that could fully load your gas turbine? Is it possible to run a turbine on very high levels of hydrogen? And again, the answer is yes, and I want to give you some examples. The picture second from the right, it has the 2 blue exhaust stacks. That's a project that General Electric did with our oil and gas division about 10 years ago. One of our customers wanted to do a demonstration project running a small gas turbine on 100% hydrogen, and that's what they did. The hydrogen was sourced from a refinery next door. The gas turbine had the appropriate modifications done to it, and they ran that gas turbine on 100% hydrogen. But that was just a demonstration project. The next project that I'm showing here, which is the last one on the right, and that picture you're kind of looking down on the gas turbine and the exhaust stack, that's a gas turbine that operates in Asia. It's a gas turbine that generates about 40 to 50 megawatts of power. That gas turbine was put in specifically to run on the waste gas coming from a petrochemical plant. The hydrogen content in that fuel varies between 70% and about 95% hydrogen. That gas turbine has been running for over 20 years, and as of this year has accumulated over 180,000 hours of operation. So it is totally commercially possible to run a gas turbine on a fuel with very high levels of hydrogen and to do it successfully and reliably. Now, different gas turbines have different capabilities for running on hydrogen, and not every gas turbine is configured the same. So this is just a snapshot of the GE portfolio. We break our gas turbines down into 4 categories. The first is aeroderivative engines. I've used that term a couple times. For those who are not familiar what that means, it literally is that we've taken the core of an aircraft engine, but now we're not using it for thrust. We now package that, connect it with a shaft and a generator, and now that actually produces electrical power. They're very small units, can ramp up, generate power very quickly, and their power output could range from as low as about 25 megawatts to over 100 megawatts. So we have aeroderivative turbines. We have our B and E class turbines, our F class, and our latest RHAs. And you can see differing capabilities depending on a number of factors on those. But the big message here is whether it's 100% capable today or not, GE has technology pathways to get all of those gas turbines in the future to running on 100% hydrogen. So as the power generation industry evolves, as hydrogen becomes more and more available, in places where hydrogen becomes that pathway to decarbonization, you can take a gas turbine and get it to running at or near 100% hydrogen and lowering that carbon footprint. Now, I do want to take a few minutes. We've talked about capabilities, but I know sometimes I get asked, well, how do you know? How do you know that you have the capability of that combustion system to burn hydrogen? You talked about how it has very different characteristics. How do you know that your combustion system will be able to operate on it? So I do want to share with you a few slides and spend a couple of months talking about our combustion facilities. This is an aerial view of one of our facilities. It's in South Carolina. This is our gas turbine technology lab. And it's one of the places where we do combustion testing of hardware. We have other facilities in the US and other places around the world where we can do testing. But this is really the prime location because we can test very large scale systems here. So as we talk about wanting to burn hydrogen or different fuels, you obviously need a supply of fuels. So this facility has a very large gas storage system associated with it. We can store all sorts of gases. You can see the picture on the right here. There's ethane tanks, there's butane tanks, there's carbon dioxide tanks. We have relationships with local industrial gas suppliers who provide us with these pure gases. And the picture on the right shows the scale of the blending system and the fuel and air management system that goes along with running large-scale combustion tests. We've got two engineers there, and you can see just the full scale of the infrastructure required to do this. This is a picture of one of our actual combustion test cells, or combustion test stands. It's actually hard to see the combustion hardware through all this because we're running a full combustion system as a full-scale production combustion system. We run it at what we call full speed, full load conditions, which means we're running it at full pressure, full temperature, and full airflow through the system. And so again, the infrastructure to manage air, that's in many cases preheated to a temperature on the order of 800 to 900 degrees Fahrenheit. In the combustion system itself, I like to use the analogy that the air flowing through that combustion system is like a race car. It's going to flow through at about 100 miles an hour. So you need the infrastructure to handle those velocities and those temperatures. And so when you look at this image, you don't really see the combustion hardware. What you see is all the infrastructure and instrumentation to do that. And then obviously, it's not just as a matter of having the physical hardware. You need the control systems to do that. This is our control room, and you can see a number of engineers preparing and running a test. We have engineers who focus on running the test. We have engineers who focus on different aspects of the test, whether it be measuring emissions from the combustion system, monitoring the combustion noise or acoustics, and different aspects of facility health, monitoring the compressors and all the different systems that go into making this run. And you can see here, if you look carefully across the top of the picture under the word data, there's a monitor, and that monitor is actually showing an image from a camera in the combustion system on that test stand. So we can actually even physically see what's happening during the test. Now, what's amazing is the amount of data that gets collected here. This system has the capability of collecting data from over 400 sensors, whether it's temperature, flow, pressure, emissions. And what I like to tell people is the test itself may only last for 4 or 6 hours, but engineers will spend 4 or 6 weeks preparing for it, and then may spend weeks understanding all the data and everything they've learned before they come back to the lab for the next test. So this facility gets used on a regular basis by many of our engineering teams as they develop new combustion systems. They push the boundaries on existing combustion systems. We try new fuels and new combinations of systems. So it really is a workhorse facility to validate the work that we do in combustion. And the reason that's important is because it gives us a window into the kind of work that we're doing as we develop new combustion systems or apply combustion systems to new fuels like hydrogen. So previously I talked about how we've been running fuels that have hydrogen on it for 30 plus years. But the truth is the combustion technology that we use is not the same as 30 years ago. There's been an evolution. I want to walk you through some of that evolution because it's important to understand where we are today, kind of the state of the art, but it's also important to understand where we started. So I'm going to walk you through the pictures on this slide. So the first picture says standard combustor. That was what we would describe as a single nozzle combustor. So in a can annular gas turbine, there would be one fuel nozzle per chamber. And that was the standard combustion system for many, many years. Back in the early 1970s, because of NOx emissions, we had to change the combustion system. And the next picture you see here is what we call our multi-nozzle quiet combustor. This is a combustion system that instead of having one fuel nozzle had 6 and provided us new flexibility. Now, all throughout here this time, other combustion systems were being developed, the so-called dry low emissions, DLE, or dry low NOx, DLN combustion systems. And those are combustion systems that provide very low NOx when operating on natural gas. The combustion systems I'm talking about here are the ones that were using hydrogen or other low BTU fuels, which were paramount for many of the industrial type applications we've worked on. Now, in the late 1990s, we were contacted by one of our customers who then was known as Norsk Hydro. Today, they'd be known as Equinor. But they came to us over 20 years ago saying, we think that decarbonizing power generation will be important in the future. Again, think about the timing. This was before the year 2000. They came to us and said, we would like to find out the implications of running high levels of hydrogen on some of our existing gas turbines. And partnering with them, we did a study in our laboratory looking at that impact. And so we ran a test on that multi-nozzle quiet combustor, and you can see there on the screen just kind of a snapshot of one of those tests. We jumped forward almost another 10 years. That combustion system is still a workhorse, and we again went back into the laboratory to explore its capability of running on high levels of hydrogen. But about the same time, this is now the early 2000s, if we think about what was happening 15 to 20 years ago, natural gas prices were slowly increasing. In the US at the time, natural gas prices was about $8 per million BTU, and we saw line of sight to natural gas prices being above $10 or being above $12, and maybe more. At the same time, natural gas prices through LNG imports into Asia were priced at somewhere between $18 and $20 per million BTU. So natural gas prices were going up and up and up, but coal prices were very low. And there was a thought that the use of coal would become predominant in many parts of the world. So the US Department of Energy decided to launch a program to look at how you could take coal after it's been gasified. Again, you create what's known as syngas, which has got hydrogen and CO, but then you remove all the carbon. So you'd have a very high hydrogen fuel. What a combustion system would look like to run on a fuel that had very high levels of hydrogen. And that work we did is what we call our advanced premixer. And that's important because that technology that was developed became the fundamental technology to anchor our next generation combustion system within General Electric. So I want to spend a moment sharing that with you because the way we do handle that combustion system, or that combustion system was developed, provides some real insight into maybe the future of burning hydrogen. So the picture I'm showing in the upper left is what a combustion system would look like if you had, let's say, an F-class turbine operating on natural gas. If you look at the center there are 5 large openings, and there's one in the center. So 6 large openings. Each of those openings basically has a premixer. Fuel and air are injected, they're mixed together, and fuel and air come out. So we have 5 discrete points of fuel injection. For a number of reasons, and some we've talked about earlier on that chart, talking about the difference between hydrogen and natural gas, under the right circumstances, hydrogen will do what we call flashback. The flame will want to propagate back upstream into those fuel mixers, and that can do damage to the hardware. So as you put more and more hydrogen in, again, its reactivity starts to dominate. So what would a combustion system look like where your fuel is predominantly hydrogen, and therefore the reactivity is based on hydrogen chemistry, etc. So we went effectively back to the drawing board. So now if we look at the series of pictures in the lower left corner, the first 2 pictures represent one of our earliest prototypes. We basically went to a facility where we could do rapid testing. That's actually at our Global Research Center, where we have our combustion group based in upstate New York. And we started doing these tests where we examined multiple configurations. We did very small prototypes, and by small, the picture on the left-hand side, that small prototype would fit in the palm of your hand. But because we were dealing with small prototypes, manufacturing very small passages was difficult. So we did something that 15 plus years ago seems intuitively obvious today, but it wasn't back then. We started making these prototypes using additive manufacturing. We were 3D printing these prototypes. And the benefit there was you could be in the lab and you could run a test. And if you decided there was some feature about that part you didn't like, you could go back to your computer, redesign it, and send it off to print. So literally, we were able to run tests, decide that we wanted different configurations, and within weeks have literally new test articles just shipped to us from the company printing them. But it also meant if you damaged a part, it wasn't that big of a problem because you could always have another one printed. Moving to the next picture in the middle there where it says prototype fuel nozzle. Yes, it's a prototype, but I say fuel nozzle, it's really a fuel nozzle assembly because each of those small holes on that face represents a point where fuel and air have been premixed already. So whereas in that previous configuration in the upper left, we talked about there were 5 discrete fuel injection points where fuel and air were premixed already. On this prototype fuel nozzle or fuel nozzle assembly, there are already hundreds of injectors, each of which has got premixed fuel and air coming out of it. Now, it continued along in our testing. We're very satisfied. So then we built an entire combustion head end, so a full combustor based on this concept. And that's the next picture. You can see there are now 7 discrete of these round nozzle assemblies. And now it's a fuel that's a very high hydrogen fuel. This continued to work so well. What we did is we took that and built not one, but built an entire gas turbine engine set of combustors. And that's the picture under the 2016 banner where it says demonstration. We took that and built enough of these combustion systems to run on a gas turbine at our facility in Greenville, and TS7 is what we call Test Stand 7. That is our full speed, no load combustion test stand. So we're actually able to run the gas turbines actually full speed, full load because we have a compressor to take load. So we demonstrated this combustion system. We demonstrated on natural gas, not hydrogen, but demonstrated this combustion system. It exceeded all expectations to the point where we commercialized it. So the final picture on the page under the 2018 banner is what the commercial version of this combustion system looks like. This combustion system shipped for the first time in 2018 on what GE calls our 9HA02 gas turbine. That turbine is at site and currently in commissioning to go fully commercial this year. That combustion system is shipping on other gas turbines going to Europe, other gas turbines going to the US. The first shipment of a gas turbine with that combustion system in the US will be later this year. But being engineers, we weren't satisfied with where we were. We wanted to go the next step. Because we knew this combustion system truly evolved out of this Department of Energy high hydrogen program, we went back to the laboratory and took the commercial hardware and said, what happens as we add hydrogen to it? At what point does the hydrogen kind of chemistry really show itself, and when do we start having some concerns? Well, it turns out that this combustion system was capable, or is capable, of running on blends up to 50% hydrogen and even a little beyond. But again, this combustion system is optimized now or configured for natural gas, not hydrogen. So we worked with the engineering team, and we know the roadmap of what would it take, or what would be required to take that combustion system today, which is 50% hydrogen capable, and take that to much, much higher levels. So the last topic I want to talk about today, going back to original themes, is what are the implications of taking hydrogen and putting it into a gas turbine, and the impact not just to the gas turbine, but to the entire power plant. Because ultimately, power plants are systems, and we can't think about the use of hydrogen in the gas turbine only. We have to think about the overall implication to the power plant. So we can think about this in terms of what is upstream of the gas turbine and what is downstream of the gas turbine. But I do want to mention one or two things about the gas turbine first. We've talked about combustion systems. Obviously, gas turbine controls have to be updated as we think about changing fuels. But the other good news is we fundamentally are not changing the compressor. We're not changing the turbine or hot section. So adding hydrogen, for the most part, really means, from a hardware perspective, all you're changing, if you're changing anything, is the combustor on the flange-to-flange gas turbine. But it's very different as we think about what happens upstream of the gas turbine. So hydrogen comes onto your site. You now have to maybe store the hydrogen. We'll come back to that in a moment. But now you bring it into your gas turbine fuel system. And now there are things we have to think about from a compatibility and reliability and safety perspective. First of all, we know that, again, if you're going to blend hydrogen in, you need a system that is capable of doing it, both hardware and the controls. We have to think about any surface that has an elastomer used for sealing, whether that's a valve, pipe flanges. Some elastomers over time degrade more substantially when exposed to hydrogen. We know that some types or some alloys of steel are more susceptible to what is known as hydrogen embrittlement. So as we think about bringing hydrogen into a fuel system, we have to make sure that the materials in that system are compatible with the use of hydrogen. We want to make sure that we have appropriate purge systems so that if we're purging, we make sure that hydrogen and air are separated typically by an inert like nitrogen, so we don't accidentally get a leak of fuel and air into each other. We need to think about safety systems. So, one that comes to mind is in a gas turbine or any plant where you're flowing a flammable gas, you're going to want to detect a leak. So you've got hazardous gas systems that monitor for leaks of traditional methane or hydrocarbons. As you put more and more hydrogen into your system, some of those detectors lose sensitivity because the amount of hydrocarbon they're looking for has gone down. So at certain tripping points or thresholds, you have to start adding detectors that are capable of sensing hydrogen leaks. Because again, if there's a fuel leak, you want to know it. And I mentioned earlier that because hydrogen's a smaller molecule, it does have a tendency to leak. So I want to walk through some of these concepts in a little more detail here. So again, right, we talked about hydrogen's a smaller molecule, just to give you a sense, in terms of molecular diameters. Here's some data on the chart. So you have to think about, how do you seal against hydrogen? Or if you are, even if you change your seal, how would you detect a hydrogen leak? We mentioned right at the beginning that hydrogen's heating value on a volumetric basis is 1/3 of that of natural gas. So depending on how much hydrogen you're doing in your system, maybe not at small amounts, but as you increase the volume of hydrogen you want to put into your system, you may have to have your piping diameters get slightly larger or larger to accommodate the additional flow so that you keep giving the turbine the required energy input. One of the things we do need to talk about is NOx emissions. I alluded to this very early on, that hydrogen will burn hotter than natural gas. The term that chemists will use is adiabatic flame temperature, kind of the temperature without heat loss. So you can see from the chart I'm showing that hydrogen will burn about 300 degrees hotter on a Fahrenheit scale, about 170 degrees hotter on a centigrade scale. NOx emissions are tied to flame temperature, and specifically they're an exponential function of flame temperature. So as flame temperature goes up, NOx production goes up even larger. And so it's important, as we think about adding hydrogen to a system, what are the implications of NOx emissions? And that's critically important for existing power plants, because they almost always have an air permit or are regulated by a local body as to how much NOx they can emit. And so as we add hydrogen to a system, we have to be cognizant of how much NOx, or what is the NOx increase, and what is the implication for an existing plant of that regulatory limit. The chart I'm showing you on the right is some raw data from our combustion laboratory. And what we're plotting is what's the relative percent increase in NOx relative to how much hydrogen was added. I tell folks, don't look at the specific points, but look at the trend. If you were 10% hydrogen or 20% hydrogen, you might be looking order of magnitude about a 5% increase in NOx, which is probably manageable with an existing aftertreatment system. You probably have some margin to your existing air permit. But now look at 50% hydrogen. That's about a 30 or 35% increase in NOx. That might be more than your aftertreatment system can handle if you have one, and it might be more than your permit. So imagine you're a gas turbine running, and your permit says you can do 25 ppm NOx, which would be about 50 milligram per meter cubed, and you had a 30% increase in NOx. So that means you're going to go up to about 7 or 7.5 ppm NOx increase. But if your permit only lets you do 25 or 26 or 27, you're now at 32 or 33 ppm. So we have to be very cognizant of the implications of hydrogen, not just to the gas turbine and its systems, but what limits, environmental limits or permit limits, exist that we might have to think about. We talked about hydrogen flammability. So here's just that, laying that out very, very detailed, the upper and lower flammability limits of traditional hydrocarbons and the upper and lower flammability of hydrogen. And again, where that matters is, imagine a scenario where you have an enclosure and you have a fuel system and you have an unintended or accidental leak. At some point, a hydrocarbon fuel, there'll be enough of it present in air, it will no longer be flammable, the so-called upper flammability limit. And you can see for most hydrocarbons, by the time you have about 20% of fuel in air, they're no longer flammable. But hydrogen stays flammable to almost 80% of fuel in air. So again, we have to think about what are the implications for this. And if we went back to the slide where I had the power plant overview, one of the things that we think about from a safety perspective is ventilation. Not so much an issue in an open space, but if you're in an enclosure, let's say the enclosure around a gas turbine, as we add hydrogen to the fuel, we want to make sure that we have the proper ventilation in that system. So if there is a leak, we continually pull enough fuel and air out and replace it with fresh air so that we don't allow that to build a flammable mixture. Now, the other component is, you may have heard people say, well, hydrogen flames are invisible. Well, they're not truly invisible, but they are very, very hard to see. The picture I'm showing here on the right, there are two pictures. One picture on the left shows 100% natural gas, and you can see the flame there. The picture on the right from the same combustor is now 100% hydrogen. You can see there, if you look very carefully, I almost say if you squint a little bit, you can kind of maybe see the flame. If this had been a darker environment, it would have been a little easier to see the flame. So it's not that they're invisible, but they are very hard to see by the naked eye in bright light. So what does that mean? So from a safety perspective, if we assume there might be a leak, and that leak might accidentally create a situation where you might have a flame, you have to have detection systems that are capable of seeing that flame, which means we're now typically looking at an IR signature or a heat signature, excuse me, a heat signature. The wonderful news is we don't have to invent those. You know, there's a large industry that uses hydrogen. If we think about the oil and gas industries, the refining industry, petrochemicals, they use hydrogen on a regular basis. So what we're doing is not reinventing these sensors. We're just using the sensors that are available commercially that allow you to see the hydrocarbons when they leak, to see the hydrogen flames. And so again, we're not reinventing the wheel. We're just using the sensor systems that enable us to do that. But it does mean as you think about putting hydrogen into your power plant, you've got to go do those upgrades from the safety perspective, not just do I change my combustion system and such. Now, I kind of said at the beginning, so, you know, I just brushed this aside, but we just say, well, hydrogen comes to your site. Well, how is the hydrogen coming to your site? Is it coming to you as a compressed gas via pipeline? Is it coming to you in a tube trailer system? Are you going to have storage at site? If hydrogen is being transported to you via ammonia, you know, as a stable room temperature liquid, how are you going to decompose the ammonia back into hydrogen? What are local regulations around bringing hydrogen? Does it change some of the safety permits that your plant operates under? And so there are lots of considerations as you think about bringing hydrogen to site, what form it's coming to you in, et cetera. And those could have implications as you think about your plant. So a couple closing thoughts, and then I know we've got some time for Q&A. So I talked about this earlier, about the implications around using hydrogen and lowering your carbon footprint. Ultimately, that's why we would use hydrogen. But because of the differences in hydrogen's heating value, both on a mass and volumetric basis relative to methane, when we think about how much hydrogen we put into a gas turbine and the carbon reduction we get from that, turns out it's not intuitive and straightforward unless you've got it set up correctly. If you were to tell me that you were going to measure your hydrogen input to your gas turbine on a mass or energy basis, the carbon reduction would be 1-to-1. So if you said by energy you were going to put 30% hydrogen into your gas turbine, you would get a 30% reduction in carbon because energy and mass are effectively the same. But almost always when we talk about fuel compositions, we talk about it volumetrically. And there, because of the difference in hydrogen energy density volumetrically, the relationship between volumetric flow rate and carbon mass reduction is not 1-to-1, and that's what this chart shows. So we think about this example. So imagine you're going to go put up a power plant, and you're going to put a blend of 30% hydrogen by volume, and 70% or the remainder of the volume is natural gas. Well, we know that hydrogen, 30% hydrogen, only displaces about 10% of the energy content. Remember, hydrogen's got 1/3 of the energy density. So if it's only got a 10% of the energy density, I'm only basically removing 10% of the natural gas by heat content. So if I look at this chart here and I say 30% hydrogen by volume, and we follow this down to where this line marks, it's at about 10 or 11%. So at low volumes or low concentrations of hydrogen, it's kind of this 3-to-1. You know, for every, you know, for volume of hydrogen, you're only getting about 1/3 of that reduction in CO2 footprint. Now, again, think about something I said to you earlier, right? If you want a 50% reduction in CO2, so if I come here and I go to 50%, it crosses this line at about 75 to 77% hydrogen. So again, if you're thinking about this volumetrically, if you want to have a 50% reduction in your carbon footprint, from a fuel composition perspective, your fuel has to be about 75% by volume hydrogen. Again, methane is incredibly carbon heavy. Methane has a molecular weight of 16, right? 12 from the carbon and 4 from the hydrogen. So it's 75% by mass methane. So I've really got to remove a lot of methane to carbon. So I have to remove a lot of methane to remove a lot of that carbon. So just something to think about as you think about doing a project where you might be doing fuel blending. And you might say, oh, I want to do 10% blend or 20% blend. Just understand that if you're phrasing that in terms of volumetric percentages of your fuel, a 20% blend of hydrogen is only going to get you a 6 to 7% reduction in CO2 emissions. So I want to make sure that we're all calibrated correctly as we think about using hydrogen as a way to reduce our carbon footprint when we're talking about low percentages. Obviously, when we talk about 70, 80, 90% hydrogen, we remove a lot of CO2, but that's not necessarily true on the low end. So I want to wrap up with just 2 final slides here. The first, just to kind of bring us back to where we started with right? The industry has tremendous experience with working with hydrogen. GE leads in this space. All of the OEMs, including GE, have continued developing their technology. At GE, we're especially proud of this new combustion system that we have and its capability to burn very high levels of hydrogen. And then GE is ready to partner with our customers. We are ready for this low carbon, decarbonized world. My role within the company after 19 years changed this year. I was asked specifically to focus on hydrogen and decarbonization. I think that's a sign of where the world is going and how important this is. We only had a short amount of time today to walk through this. There's a lot of material that is available. I want to point you to a particular website from the GE perspective. We have white papers available. We have done multiple webinars. We have tools available to do some of the calculations I showed you about CO2. This is a website that's available to the public. These materials are available. I encourage you, if this is something you're interested in, if you want to learn more about what GE is doing in this space, I encourage you to look at this website, look at the material there. I will put my contact information up. If you do have follow-up questions, I can be reached on multiple different platforms. But I do know that we have time for Q&A today. And I think at the moment, I'm going to pause and take a quick drink as we transition over into Q&A.
Yeah, okay. Thank you, Jeffrey. Thank you very much for your presentation. Very good presentation, very detailed and very interesting also. Yeah, we can see that hydrogen for General Electric is a history of more than 30 years. So you see, I think it's important to extend this experience so that power generation companies and governments understand that hydrogen has been used and handled safely for a long time. There are people prepared and trained to face this type of projects, and which open the door to 100% decarbonization of energy generation. I think that's possible. Yeah, one question was this presentation will be available in order to share other people. It's possible to have.
Yes, we can definitely make this this presentation available.
Okay, perfect. Yeah, we have a lot of questions. We have received a lot of questions. We will start with. Let me see. Okay. Oh, very technical question. How do you solve the lower volumetric energy density of hydrogen to generate the same energy that will be generated with natural gas? Higher hydrogen pressure, higher flow, partial load, and when you consider 100% of hydrogen concentration. Could you explain about that?
Yes. So as the person asking the question has rightly understood, that the volumetric energy density of hydrogen is lower than that of natural gas. So the primary way of solving this problem is you have to flow more hydrogen in order to get the same energy density. In an existing gas turbine, you really can't increase the pressure of the system dramatically because it's been already configured for operating at a specific pressure. So what you have to do is you have to add more fuel to get the same energy content on a per mass, per volume, but really it's on a per time basis, whether it's pounds per hour, kilograms per hour, cubic meters per hour. You've got to get the same energy density into that system. The good news is fuel only represents a very small portion of the total flow going through a gas turbine. So increasing the volume of fuel doesn't mean that you've somehow impacted the overall operation of the gas turbine. Gas turbines can handle, some amount of more flow, and typically we're talking about the amount of flow we're adding here is typically within that boundaries. And there are other ways to handle it, but yes, the primary answer to the question is you add more flow, you add more fuel.
Okay. What is the percentage difference in the price of a turbine with operation on 100 hydrogen, considering its necessary modification, of course, versus the same turbine operating with natural gas? Yeah, he is talking about the retrofit of this kind of turbine and compare the price, the final prices. Cost, sorry.
Yeah, no. So anytime you take an existing gas turbine and you want to add hydrogen to it, there's additional cost. You have to make modifications to the accessory systems, how you handle the hydrogen. You may or may not have to change the combustion system. So there's no simple one answer because it also depends on how much hydrogen. If it's a very low amount of hydrogen, let's say 5%, the changes may be very minimal. If you said you were going to go from running on natural gas to want to run on 100% hydrogen, you have to change your combustion system. You're most likely going to need an entirely new fuel system. And so that cost starts to get larger, but it is no way near kind of, let's say, the cost of replacing the whole gas turbine. Let's put it in kind of order of magnitude perspective. And it's a very different scenario if you're talking about if you're going to order a gas turbine and you wanted that gas turbine to be able to run on hydrogen from the beginning. Because as I said earlier, we're not changing the compressor, we're not changing the turbine section, we might be changing the combustion system. So yes, maybe there is a price delta between the combustion systems. You might have to see some additional fuel accessories, some additional safety systems, so that increases price. But we're not talking about, if we think about what's expensive in a gas turbine, the compressor is very expensive, right? Very, equipment rotating at very high speeds. And then the hot section, which has to not only withstand the rotational speed, but a very high, temperature environment. Those sections on the gas turbine aren't changing. So if you say, I want to buy a gas turbine that's going to run on hydrogen versus natural gas, yes, there's a price increase, but it's not the same as, you are not doubling the price of the turbine, let's say, right? There's an increase, but it's commensurate with the kind of systems that are changing, and we're not changing the most expensive systems.
Yeah, of course, you have other advantages. And what is, talking about the cost also, and what is the distribution of cost, investment, operation, maintenance, administration costs, etc., of hydrogen power plant compared with the conventional natural gas plant? This share or this portion or this percentage change or not?
So let's break this up into two buckets. I love this question. Let's talk about capital cost versus operational cost. As I said from the last question, this is great that the questions are coming in this order. The capital cost is not that dramatically different. Operating cost is hugely different, and it's fundamentally because of the price of hydrogen. So let's have that conversation for a moment. So today, if you were to look up spot prices of natural gas in the US, it's about $2 per million BTU. If you looked at what LNG prices were, that might range between $4 and $6 per million BTU, depending on where you are, local transportation costs, etc. So let's talk hydrogen costs. Again, there are different ways of making hydrogen. If you wanted to get hydrogen today that wasn't green, meaning it's hydrogen produced via natural gas or coal, and you don't do anything with the carbon, you just emit the carbon to the atmosphere, that's probably, depending on how far you're transporting it, somewhere between $5 and $10 per million BTU. But the whole point of using hydrogen for power is we want it to not have carbon associated with it, right? Because if I didn't care about the carbon, I would just keep using natural gas. But I want hydrogen that comes from a source where there either is no carbon or the carbon has been captured and sequestered. So if I look at traditional methods of making hydrogen, And steam methane reforming is one of those, and it makes something like 70 or 80% of the hydrogen in the world today. If you took that kind of system and added carbon capture to it, that easily puts you in the $10 to $15 range. And again, I quote everything in dollars per million BTU. So if you had very expensive natural gas at $6 and you had to go to gas at $10 to $15, you've now doubled your fuel price. And doubling your fuel price doesn't quite double your cost of electricity from the plant, but close to it. So your life cycle cost of your power plant, is almost double. But that's optimistic. Green, that blue hydrogen, and that's what this is called. Hydrogen from steam methane reforming with carbon capture is defined as blue hydrogen today. And again, $10 to $15 is the low range. It might be as high as $20. In which case now that could be a 4x increase in your cost of fuel, which then represents a 3 to 4x increase in your cost of electricity. Now, if your ultimate goal is green hydrogen, and again, that's hydrogen that is produced from electrolysis using renewable power. So there's no carbon in that system at all, theoretically, from a production perspective. Today, if you were to look at green hydrogen today, depending on whether you said it was curtailed power or dedicated power, and how much the electricity costs, you could be looking at hydrogen prices optimistically as low as $50 per million BTU, but I've seen prices as high as $100 per million BTU. So imagine, again, I'm going to take a US example, right? So imagine you're buying natural gas today at $2 and someone told you can get fuel at $40. Well, that's 20x my fuel price. And since fuel typically is the largest single element in cost of electricity, if you do a cost of electricity analysis, fuel is the single largest component because you have to buy lots of it year over year over year, and it tends to be millions of dollars a year depending on the scale of your power plant. So imagine you were buying fuel at $1 million a year, but all of a sudden you have to buy fuel now at $20 million a year. That's a huge increase on your operating expenses. And so the challenge and the question is, what's the distribution of cost? Today, most of what you spend on a power plant is fuel. But if you go to hydrogen, that percentage will grow because of the cost of hydrogen relative to natural gas. Now, in the future, we definitely see pathways for hydrogen costs to come down. There are lots and lots of studies that talk about this, bringing the cost of electrolyzers down, increasing the production of electrolyzers to help bring costs down, getting large installations of solar and wind with very low electricity prices, which again bring down the cost of hydrogen. So there are lots of studies that show a pathway to getting lower and lower cost hydrogen. But still, the largest cost element in operating a power plant will always be fuel. Even today, natural gas prices where they are, it's the single largest element. Hydrogen only kind of amplifies that.
Yeah, thank you. Are now changing the topic to compensate for the difference in inertia between natural gas and hydrogen. What parameters of variables were most effective?
To be honest, I'm not sure what the questioner means by the term inertia. What I'll say here is, again, there are differences in heating value between the two fuels. We know what those differences are and can compensate for that with additional mass flow. We know how to get the control systems and the accessory systems configured to handle that. So again, I'm not sure I'm answering the question properly, but we believe that how you manage hydrogen is possible. Again, we've done demonstrations and we have commercial projects that run very, very high levels of hydrogen. So I think this is a solvable problem.
All right. Talking about the cycling, what is its ramp-up time of hydrogen gas plants? Is a good idea to use 100 hydrogen for backup plants, for example, maybe to complement the renewable energy generation? The behavior of the hydrogen in a turbine is the same of the natural gas in this sense.
We believe that ramp rate, again, so for folks so ramp rate is the rate at which you increase power, typically measured in, let's say, megawatts per minute. You know, from, let's say, starting a gas turbine or a gas turbine at low load to getting the gas turbine up to its base load. And where that's important is you think about connecting gas turbines with renewables. So as renewables will vary, and that's their nature, they're variable sources, you want something else on the grid that as renewables come down rapidly, something else comes up rapidly to balance the grid, and vice versa. You know, you can just imagine the scenario where it's a beautiful sunny day and you have lots of solar, and then all of a sudden it's very cloudy, and that we all know that can happen in just minutes. So as all of a sudden that solar power would ramp down, you would say want a gas turbine that can ramp up just as fast. Our view is there's really not going to be very much, if any, difference in running a hydrogen gas turbine from a natural gas turbine in terms of ramp rate. We think that's going to be the same. And as we've talked with customers who are blending fuel already, we think that's easily doable. And we think about turbines like our aeroderivative gas turbines. Again, these are the ones that are based off aircraft engines. If you've ever sat in an airplane near the wing and you hear that engine spool up when the engine has started, how fast that comes up to speed. You know, think about putting an aeroderivative engine that can run on hydrogen in that scenario. It automatically, by its nature, has the ability to ramp up and ramp down very fast. And now imagine that gas turbine running on hydrogen and its ability to ramp up and down as renewables are varying. So I think it's a great question. We see, you know, little to no difference in that in the future.
Okay, and talking about the NOx, or the emissions, we know that the combustion temperature of hydrogen is higher than natural gas. What type of material or coatings should be used in the turbine, into the turbines, to protect the hardware, etc.?
Yeah. So here's an interesting statistic, kind of data point. So if you look at a gas turbine today, and these very large modern gas turbines, and think about the temperature that the combustion exhaust leaves the combustor and goes to the hot section, the turbine section. Today, that temperature is already hotter than the melting temperature of the metals. So today, you have to actively cool the first and second stage of the rotating equipment. You have to have ceramic coatings and other coatings that basically can absorb the heat so it doesn't get to the base metal. So already we're in a world, regardless of hydrogen, that we have pushed these gas turbines to the point where we have to protect the base metal already. So we're actively cooling some of these parts. We have ceramic coatings. We have, some are sacrificial coatings. Some are thermal coatings. And now you say, okay, so now I have to go to hydrogen. Well, yes, hydrogen will add some additional heat, but I'm already protecting those parts from that very, very challenging environment. So what does that mean? I might have to increase the cooling flow a little more. I might have to put a slightly thicker coating on, but we already have that process in place. We're doing that today already. So this is just, again, will amplify kind of what needs to happen there. But we're already doing that. We're already actively cooling these parts and such. So it's a great question, but I think that's a challenge that's well understood.
Okay. And regarding NOx, what is the trend in NOx emission for the turbine start and stop state versus its stable operation or nominal operation? Should differentiate limits to be considered by mode of operation between the start-stop stage and then a nominal operation? They are a big difference or not?
I think you absolutely have to consider startup and shutdown separate from base load. There are, as you start up a gas turbine, it goes through different regimes. These are typically very transient regimes. They don't last for very long. But I think you do want to, when you talk about measuring NOx, if you have a gas turbine, especially one that is really running all the time, I think you want to focus on the base load NOx. What we want to be wary of is being overly restrictive in a way that limits gas turbine operation. So my view is that we have to be cognizant of NOx emissions and limit them where we can, but we have to balance that with appropriate regulation.
Okay. Other questions relate to the control of NOx emission. I'm not sure you use this method. That how much does the NOx gas generation change as a percentage when using water injection, WLE, in the gas turbine. I'm not sure you use this kind of control.
Yeah, so it's a great question. So in the use of water injection or some other dealing, it could be water as a liquid, could be steam, right, water vapor, or even nitrogen. That is used actually in the industry pretty regularly for control of NOx, but it's typically used in what's called these diffusion flame combustors. So thinking about today's presentation, what GE would call the standard combustor or this multi-nozzle quiet combustor, there you can take those combustion systems, if you let them run without diluent, would make NOx on the order of 200 to 400 ppm. Because they're diffusion flame combustion systems, they burn very hot. We inject water or steam or nitrogen, and we can bring that NOx down to somewhere between 42 and 25 parts per million. So you can use, let's say, water or steam injection to actively control NOx. But there's also a disadvantage to that, because you have to source the water from somewhere or the steam from somewhere. If you're a combined cycle plant, and again, for those who use a term, so if you take a gas turbine and just let it run normally, we might consider that simple cycle or open cycle. It runs, and whatever heat goes out the exhaust stack. If you put a heat exchanger on that exhaust stack to extract the kind of that leftover heat, you can use that leftover heat to boil water, and you can use that boiled water, that steam, now in a steam turbine to generate extra electricity. So we call that combined cycle. The beauty of that is you have this almost this waste energy that would go up the gas turbine stack, and you capture that and you make a more efficient plant. So let's go back to this question of using water or steam. So imagine I'm a combined cycle plant and I'm running a certain efficiency, but now I'm going to take some steam or some water from that combined cycle, from that steam turbine or the heat exchanger, because I'm going to use it for dilution in my combustor. The good news is I lower my NOx, right? I put more mass into the gas turbine, so I make more power. But because I've stolen some of that steam from that combined cycle component, I actually lose a little efficiency, because I've taken some of that free energy and I'm not using it for power anymore. So there's a trade-off between output, NOx, and efficiency in this system. But to answer the kind of the original question, yes, you can work to control NOx emissions by the use of water injection, but you have to be careful. There's a limit to how much water you can also put in the system before it actually starts to have other impacts, not just around NOx. You can impact gas turbine operability. So again, there's a balance of how much you put in.
Okay, thank you. There is a question: could be possible to explain the ignition process using a 100% hydrogen combustor?
So ignition varies. There are different ways to ignite things. Some gas turbines will ignite every single combustion chamber. Other gas turbines will ignite one gas turbine chamber and allow to basically take the heat and use that to ignite the next one. Some folks in the industry will use spark plugs. Some will use kind of small torches, basically as a pilot flame. So there are lots and lots of ways to do that. Because there are no true commercial 100% hydrogen turbines out there today, I don't want to speculate on what a future technology would be, but there are lots of technologies available today that could be applied to that.
Yeah. What is the optimal way for hydrogen storage in case of 100 use of gas turbine? There exists a local storage, or just to use the gas from pipes, etc.?
That's also a great question. So let's talk about hydrogen transport first, and then because that lends itself into the question. So you've made hydrogen, now you need to transport it to the end user, whether it be a power plant, or maybe it's the local gas station because you've got fuel cell vehicles. It depends where you make the hydrogen, how close versus how far. So once you've made hydrogen, you can transport it in one of multiple ways. You can transport it as a highly compressed gas. Typical hydrogen storage or tankers are somewhere between 5,000 and 10,000 psi. You could transport it as a cryogenic liquid. Transporting hydrogen as a cryogenic liquid, I know this in Fahrenheit and Kelvin, but not in Celsius. So it's something like minus 420 degrees Fahrenheit, which is 20 degrees Kelvin. And so it's incredibly, incredibly cold. So it places a huge burden on the system to transport it cryogenically. As I kind of alluded to earlier, there's a lot of work being done in could you transport hydrogen as an organic molecule? It's transform it either into ammonia or some other organic molecule, which is a stable liquid at room temperature. So depending on how you're getting the hydrogen, how do you store it? So if you get it as a high pressure gas, obviously you would need either storage tanks or as the listener kind of, as the questioner has alluded to, if you have a large gas network, could you store it in the piping? And the answer is yes. Think about this. In many countries, the natural gas storage system is actually the gas distribution system. There's huge volumes in that system. Yeah. Of course, today we don't have a hydrogen distribution system. We would have to create that. If you transport hydrogen as a cryogenic liquid, at some point you're going to want to not have it be a cryogenic liquid and create it and move it back into a gas. If you were to transport hydrogen as a stable liquid like ammonia, you could just have an ammonia tank. Ammonia, as an example, right, is viable. Other folks are looking at complex molecules. The challenge with ammonia is ammonia has its own toxicity issues. So storing and transporting ammonia does bring its own challenges. When we talk about long-term storage of hydrogen, there's a really interesting concept. Today in the world, when you have large amounts of natural gas that need to be stored, they're not only just stored in the pipeline, they're stored in underground caverns. That's done in Europe, it's done in the US, it might be done in South America, I don't know. But these are fairly large caverns that have been basically configured to store gas at reasonable pressures. There's work that's been done in the US and other parts of the world to do the same thing with hydrogen, examining, what would it take to store hydrogen in these underground reservoirs. The value there is, if you imagine hydrogen is a way of time-shifting renewables. So imagine you're in a country that has an incredible wealth of solar in the summer months, in the spring and summer and fall, and you have so much solar that you have more than you can really use. So how do you deal with that curtailed power? You don't waste it. Maybe you make hydrogen and you store the hydrogen. Why do you store the hydrogen? Because in the wintertime, maybe you have the opposite problem, that you have so little solar for certain periods of time that you now need to figure out a way to keep the energy grid running for periods where you have called a solar drought. Well, if you store hydrogen in the summer because you had a glut of solar, you've made all that hydrogen, maybe now that hydrogen is a way you time shift renewables. And now in the wintertime, you can use all that stored hydrogen to help supplement the grid by running it through your gas turbine. So in that scenario, you need more than just the grid or a tank. You need very, very large storage systems, that could store, days or weeks or months worth of hydrogen. And so that's where this concept of underground storage comes into play, because it really does give these massive volumes that you wouldn't want to reproduce in, let's say, a tank farm.
Yeah. The time is running. And in Chile and Germany, there are plans to remove the coal plant from the electrical system until 2050 and 2038, respectively. Do you think it's make economic sense to convert these coal plants into gas plant, and then that they can burn hydrogen in the future?
I really can't speculate on the economics of does it make sense to take a coal plant and replace it with a natural gas plant, because the regulations, the economic scenarios in each of these different countries vary so differently. What I can say just from a technical perspective is, can you take a coal plant down and replace it with a gas plant? Yes. Can you take a gas plant and make sure that over time that gas plant can evolve? Whereas today it might start running on 100% natural gas, but over time you upgrade it so eventually it's running on 100% hydrogen? Absolutely. So if the concept is replace coal with natural gas plants, and those gas plants become your future pathway to burning a carbon-free fuel, technically viable. The economics are a different discussion.
Yeah, I think. Maybe 1 minute more. What will be the General Electric's next step in increasing the number of the customers, including Chile, that can burn hydrogen in their turbines? What is missing to take this step cost, understand hydrogen management, etc. What's your vision, or the vision of your company?
So we're committed to working with our customers who want to be forward-looking, who have a vision. We announced a partnership yesterday in the U.S. with one of our customers. They have a gas turbine that gas turbine isn't even in commercial operation yet. The gas turbine has been shipped to site. We're getting all the systems in place to start the gas turbine on commercial operation next year. And the customer announced already this week their plans to start blending hydrogen in. So we are looking for ways to support our customers from the technology. Ultimately, if we can figure out ways to bring the cost of hydrogen down or provide the technology, ultimately, much of this will depend on what local regulations are. Is there a carbon tax? What the economic incentives might be? But we're here ready to partner with our customers. We have the technology. So if there are customers in Chile who are thinking about the use of hydrogen and gas turbines, we'd love to have the conversation about, how do we help them in that transition going, towards this decarbonized future.
Yeah, thank you. Unfortunately, the time is up. It's possible to send you some question after the event. We have a lot of questions, but we will try to aggregate or to resume this question. It's possible to have a feedback after the event.
Absolutely. If you send me the questions, I would be happy to go through them and provide you answers that you can distribute to the audience.
Perfect. Okay. Thank you very much for your presentation, your answer. Very, very interesting, and very appreciate your help. And thank you very much again. And see you, or we will be in contact. Okay?
Excellent. Thank you so very much.
Thank you, Jeffrey.
Okay. Bye.
Bye. Para todo lo demás, muchas gracias por la audiencia, muy buena audiencia, considerando que este es un tema bastante específico. Así que estamos súper contentos con la cantidad de preguntas que llegaron. Como dije, vamos a tratar de recolectarlas, vamos a tratar de abreviarlas y poder enviárselas a Jeffrey para que las tengan. La presentación estará disponible, vamos a hablar con Jeffrey para que la disponga lo más pronto posible. Este video también va a estar disponible, de tal manera que ustedes puedan revisarlo o puedan enviárselo a alguien que no pudo asistir. Así que le agradecemos nuevamente, muchas gracias, y nos encontramos en 2 semanas más para otra taller técnico. Así que muchas gracias a todos y muy buen día.